Hello students, have you ever wondered what exactly keeps common salt, the white crystals on your dining table, so stable? Why doesn't it just crumble into sodium and chlorine again? The answer lies in one of the strongest forces in chemistry, the electrovalent bond, also called the ionic bond. In such a bond, electrons are not shared like in covalent compounds but are completely transferred from one atom to another. Metals, which love to lose electrons, transfer them to nonmetals, which eagerly accept them. This exchange creates positively charged cations and negatively charged anions, and the strong electrostatic pull between them holds the compound together. That is why compounds like sodium chloride, calcium oxide, and magnesium chloride are so stable and widely used in our daily life. Let's begin with sodium chloride, the compound we know as table salt. Sodium has an atomic number of 11, giving it the electronic configuration 281. That single electron in the outer shell makes sodium unstable, so it readily loses that electron to form a sodium ion, written as Na+. On the other hand, chlorine has an atomic number of 17, with a configuration 287. Just one electron short of a stable octet, chlorine easily accepts sodium's electron to become chloride, written as Cl-. The reaction can be shown step by step. Sodium gives Na++ electron, chlorine plus electron gives Cl-. Overall, Na plus Cl gives NaCl. The strong electrostatic attraction between Na plus and Cl- ions creates a robust ionic lattice. That is why sodium chloride has a high melting point, dissolves easily in water, and conducts electricity in molten or aqueous state. As you see on screen in the electron dot diagram, the one electron moves from sodium to chlorine, making both atoms stable. Now, let's look at calcium oxide, a key ingredient of cement and mortar. Calcium, with atomic number 20, has an electronic configuration 288. It loses 2 electrons to form a calcium ion, Ca2+. Oxygen, with atomic number 8 and configuration 2,6, gains those 2 electrons to complete its octet, becoming oxide, O2-. The reactions can be written as calcium gives Ca2+ plus 2 electrons. Oxygen plus 2 electrons gives O2-. Overall, calcium plus oxygen gives calcium oxide. These ions lock together in a lattice of Ca2+ and O2-, forming a hard crystalline compound. The electron dot structure you see here shows calcium donating 2 electrons to oxygen, making both ions stable with noble gas configurations. Another classic example is magnesium chloride. Magnesium, with atomic number 12, has a configuration 282. It loses 2 electrons to form Mg2+. Each chlorine atom with configuration 287 accepts 1 electron. So, magnesium bonds with 2 chlorine atoms, giving us magnesium chloride. The reaction can be summarized as Mg gives Mg2+ plus 2 electrons. 2 chlorine atoms plus 2 electrons give 2 chloride ions. Overall, Mg plus Cl2 gives magnesium chloride. In the electron dot diagram, you will notice magnesium donating 2 electrons, 1 to each chlorine, forming 2 MgCl ionic bonds. This compound is found naturally in seawater and used in industries as well as in medicines and de-icing salts. What do these examples teach us about electrovalent compounds? First, they are crystalline solids with very high melting and boiling points, a result of strong electrostatic forces. Second, they dissolve in polar solvents like water but not in nonpolar solvents such as kerosene. Third, in the solid state they do not conduct electricity because the ions are fixed in place. But in molten or dissolved form, they are excellent conductors as the ions are free to move. These properties explain why ionic compounds like salt, lime, and magnesium chloride are so useful in everyday life and in industries. Let's quickly work through the bonding process in sodium chloride step by step. Step 1. Write the configurations. Sodium is 2, 8, 1. Chlorine is 2, 8, 7. Step 2. Sodium donates 1 electron, becoming Na plus with configuration 2, 8. Step 3. Chlorine gains that electron, becoming Cl minus with configuration 2, 8, 8. Step 4. Combine Na plus and Cl minus to form NaCl. Step 5. Confirm stability. Both ions now resemble noble gases, sodium like neon and chlorine like argon. This stepwise process shows clearly how the stability of the compound comes from the transfer of electrons and the resulting noble gas configurations. So, let's revise. An electrovalent bond is formed by complete transfer of electrons, creating oppositely charged ions held together by strong attraction. Sodium chloride is formed by transfer of 1 electron, calcium oxide by transfer of 2 electrons, and magnesium chloride by transfer of 2 electrons to 2 chlorine atoms. Electrovalent compounds are hard solids with high melting points, soluble in water, and conductive in molten or dissolved state. Their electron dot diagrams are a visual proof of how atoms achieve noble gas stability through ionic bonding. And remember, from the pinch of salt you add to food to the cement that holds your buildings strong, ionic compounds surround us in our daily life. I hope this session helped you see how ionic bonding is not just a chapter in your textbook but a real force that shapes the materials around us. In the next class, we'll explore even more fascinating concepts of chemical bonding. Until then, keep observing chemistry in action. It's happening everywhere around you.